So proton NMR, right? So I'm just going to cover this as quickly as possible. This is nuclear, magnetic, and resonance. What happens in proton NMR is that you've got protons and neutrons. Any nucleon that you have in the nucleus, they have a magnetic spin or a magnetic dipole moment. What that basically means is that, that's known as a spin. What that simply basically means is that if you have a proton or a neutron or any nucleon, remember we are talking about nucleons here. So whenever we have nucleons, they have a particular magnetic field. So for example, if I draw, just a second, if I draw a proton, so think of this as a tiny proton. This proton is going to have a magnetic field. It will have a charge, but it's also going to be acting as a tiny magnet. So think of these nucleons as tiny magnets. Now, nucleons are paired. In an atom, nucleons are paired.
Sir?
Yes.
Sir, in nucleons, there are neutrons and protons?
How? So I'm referring to both. Any particle that's in the nucleus, that even electrons have spins, they have magnetic fields. Well, this is not the literal spin. What it simply means is that every elementary particle has a magnetic field. And it's going to act as a tiny magnet. So it not only does it have a charge. For example, if this is a proton, it will have a charge of +1. So that's an electrostatic force of attraction. It's going to have that, but it will also have a magnetic field associated with it. Is this clear?
Yes.
Achha, so abhi hota hai ki if you have nucleons which are paired, then they would always have opposite pairing, which means that if one is pointing upwards, the other one would be pointing downwards. So that means the magnetic fields would cancel out. So magnetic dipoles, they cancel out because they have opposite spins, which means it's not going to show any magnetic field. The nucleus will not show any magnetic fields. So even if you have even nucleons, this is always that happens. The dipoles, they cancel out. Now the thing is that if an element has odd number of nucleons, so what's going to happen is that the dipole magnetic spin will not cancel out. So overall, the nucleus will have a magnetic field. For example, one very important element is hydrogen. In its nucleus, it's got one electron. So it has this nucleus, plus it also has an electron that's surrounding it. Now, remember, we're not interested in the electron, we're only interested in the nucleus. So the nucleus of a hydrogen has just one proton. So it will have a magnetic field, and that magnetic field, and let's assume that the electron is lost. So let's assume that the shell is also gone. So it's just a nucleus with one proton in it. So the proton will have a magnetic field. And that magnetic field, just like a magnet, could be pointing anywhere. So at this moment, it can point anywhere. Its magnetic field is not going to cancel out. So you can think of hydrogen protons as tiny magnets. Now, the reason the hydrogen is important is that hydrogen is everywhere. Most molecules, especially organic molecules, they have hydrogen. Okay? It's literally everywhere. Like all acids have hydrogen. I mean, lots of things. Water has hydrogen. So it's one of the most abundant elements. So most organic molecules have hydrogens in them. So which is why we study that. And it gives you the magnetic field of a hydrogen proton gives you a lot of information about the environment that's around it. So for example, you've got a CH4 molecule. Okay, remember, we can't see these molecules. The only way we can figure out the structure of these molecules is by guessing properties. Because how can we figure out that they're like telescopes or your microscopes are not that good that you can see a structure of an atom exactly like this. So the thing is, most of it is just guesswork based on whatever you get, whatever little information that you get from this proton NMR. And so right now, you've got a CH4 molecule. All these hydrogen atoms are existing as tiny magnets, and the magnetic fields are pointing in random directions. So what they do is that they take a big magnet. For example, there's a North Pole. Most MRI scanners are kind of like big magnets. So what they do is, on one side there's a North Pole, and on the other side there is a South Pole. They put the CH4 molecule into this powerful external magnetic field. Now, what happens when you put a CH4 molecule into this powerful external magnetic field? What's going to happen is that there would be strong. Now and let me change. So it's present in this strong. There's an external environment now. I mean, the CH4 molecule is not just present. There are these strong magnetic fields in which this molecule is now existing. And all those magnetic fields are pointing toward from north to south. So that's known as your external. That's known as your external magnetic field. Is this clear up till this point?
Yes, sir.
So what will happen if you introduce an external magnetic field, just like a compass needle? Where does the compass needle point by default? It points to the north, right? It aligns with the external magnetic field of the Earth. That is what the compass needle does. I mean, your tiny hydrogen protons are also acting as these tiny magnets. So what's going to happen is that they're going to align with this powerful external magnetic field. So they're going to align with it, and they would all start to point in the same direction. Just like a compass needle, all of them would start aligning themselves with the external magnetic field. That's what magnets do. This is known as a low energy state. Or it's known as aligned spin. So basically all your hydrogen protons are aligning with the powerful external magnetic field. The nucleus of the hydrogen atom is known as the proton because there's only one proton in it. So that's our low energy state. Now, and this is the default state. Just like a compass needle, all the compasses would start pointing towards the Earth's north. The same thing happens over here. All the hydrogen protons would do exactly the same. Now, what happens is you can make these protons energetic. You can give them energy in different ways. What you could do is you could give them energy in the form of radio waves. And this is going to make this hydrogen proton energetic. Now, when it's energetic, what you can do is when this hydrogen proton gains a lot of energy, it can now possibly oppose the external magnetic field. It can go and start opposing the powerful external magnetic field, but it has to be very energetic. Just like a compass needle, if you want to make it point in the wrong direction, you would have to do it forcefully. It needs to be energetic. I mean, you would be the one that would be providing the energy. So that is known as the high energy state. So high energy state is that's known as opposing spin. And in this high energy state, the H protons oppose the external magnetic field. But they need to be very energetic for that. Because by default, the magnetic field would make them point in the towards south. But if the radio waves are providing them energy and they gain energy, then the more energetic protons would start opposing the external magnetic field. Is this point clear? The two energy states.
Yes.
Yep. Yes.
Achha, so at the quantum level, there's just two states. I mean, you don't have a lot of energy states like in the real world. You could make the compass needle point in any direction. But in the quantum world, there's just two directions. It's either aligned with the external magnetic field or it's opposing that. There's just two energy states. There's low energy state and there's high energy state. So there's not a lot of choice. Okay? So remember, energy levels for these elementary quantum particles, they're very fixed and discrete. Okay? For example, a compass needle, you can force a compass needle to point in any direction, not just the opposite direction. You could make it point to the top, okay, in the real world. But in the quantum world, they're just simply two states. One is the line state, and the other one is the opposing state. The energy levels are very discrete, and they're just two energy states. Now, this is known as resonance. This whole process is known as resonance. So we'll say that the hydrogen proton is resonating. And there is an energy gap. The electron needs a very specific amount of energy to do this, to go from the low energy state to the high energy state and back again. So the proton needs to gain a very specific amount of energy. It's not, the other thing about quantum particles is that they always gain very specific amounts of energy. It's not like you give it energy, any energy, and it's going to absorb that. So the states are very discrete. So discrete means that they're very unique states. It's not that you can do anything, it's just two states. And a very, very specific amount of energy needs to be given to the proton. Now, remember, energy is proportional to frequency. So since every proton for resonance would absorb a very specific frequency from the radio waves. So the radio waves come in, they're not going to absorb any frequency. It's just going to be a very specific frequency. So it depends on the energy gap. So a very specific frequency is absorbed. When an H proton resonates. From the radio waves. So if they need more energy, a higher frequency would be absorbed. If they need less energy to resonate, a lower frequency is going to be absorbed. So is this clear that these hydrogen protons are resonating and they would be absorbing a very specific frequency from the radio waves? Is this clear?
Yes.
So moving on, what does this delta E depend on? Factors that affect and if delta E is affected, then the resonating frequency will also be affected. If the delta E becomes bigger, like it becomes more difficult for the atom to resonate, and the energy needed is a lot more, then the frequency absorbed would also be greater. So factors that affect delta E. So look, have a look over here. Now, one factor is the external magnetic field. For example, if I increase the strength of the external magnetic field, like if I do this, so if I do this, that I increase the external magnetic field, and the external magnetic field is now a lot stronger. So what's going to happen in this case is that it would become much harder for the protons to resonate. Is this point clear? That a stronger magnetic field, it would be a lot more difficult for the hydrogen to point in the wrong direction.
Yes.
Okay. So factor number one is the strength of the external magnetic field. So you've got what you're going to have is stronger external, more powerful magnetic field. Then it's going to be more difficult for the hydrogen proton to go into opposing spin. It's a lot more difficult to go into opposing spin, and that would lead to a higher resonant frequency. More energy needed. So a higher resonating frequency or a higher frequency would be absorbed. So first point, is this clear? Adam, is this clear? Ethan, is this clear?
Yep.
So now the second factor, this factor is not that important. The second factor is the one that's important. That's known as the chemical environment. Or we can say that that's known as the shielding effect. So this factor is way more important. And this one provides information about the structure of the environment around the atom, or around the H proton to be specific. So here we have an H proton that's so here's my proton, and this proton it's in a line spin. So there's this powerful external magnetic field. And it's aligned. Now, what's going to happen is that this proton at the moment is experiencing a lot of magnetic field. And so a lot of powerful So kind of difficult for the proton to resonate. So it experiences. This means it's less shielded, which means it's kind of exposed. Like the whole proton is very exposed. So this is less shielded and experiences more external magnetic field. So difficult to resonate, and a higher frequency would be needed for this. But then there's another one. There's going to be another type of proton, and in that case, let's say that proton is not as exposed as this one. What I mean by that is a lot of times hydrogen has an electron around it. What does that electron do? That electron would, in a way, kind of deflect the magnetic fields. And let me just draw that completely. Like, let's ignore this. So let's assume so I've rubbed off all the magnetic field lines. And now let's assume there's an electron that's roaming around it, and that electron is forming an electron cloud around the H. So there's an electron that's surrounding the proton, right? Now that electron would, in a way, deflect the magnetic fields. So it's like shielding. So the magnetic field lines would come in, but they're going to get deflected by the electron. So this is what's happening now. That means the proton is not actually experiencing a lot of magnetic field, because the electron around it is kind of shielding the proton. So this one is more shielded. And all your external magnetic fields just hold on 1 second. So all your external magnetic fields, they are deflected. So proton experiences, in this case, a smaller magnetic field. And it would be easier to resonate. It would be easier to resonate. And so in the first one, there's going to be a higher resonant frequency. And the second one is going to be easier to resonate. So it's going to be a lower resonant frequency. I mean, you don't need to really care about the resonant frequency. You just need to understand the concept behind this, which is that if the proton is not surrounded by electrons, the frequency of resonance would be different. If the proton is surrounded by electrons, the frequency of resonance would be different compared to the first one. Is this point clear?
Yes. Yeah.
Okay, so the resonant frequency would change. And so a lot depends on the electron shielding. Now the electron shielding frequently changes because these atoms are not isolated. Most of these atoms are part of compounds. So the environment frequently changes. Sometimes the hydrogen proton is away from its nucleus. So just a second. So sometimes what would happen is, like in an HCl atom or HF atom, if you have an HF atom, the electron of hydrogen is very close to It's very close to fluorine. So that kind of indicates that the proton would be very less shielded. Is this also clear? Adam, is this clear? Amna, is this clear?
So could you repeat one more time?
Yeah, I'm just saying that you do get the idea, right? That what the electron would do. That
Yes.
it would dissipate or sort of scatter the magnetic fields that are approaching it, and the proton will not be experiencing a lot of magnetic field, and it would be easier for it to resonate and go into opposing spin. For the first one, it would be difficult to resonate. Now, this one is that the hydrogen proton shielding changes a lot. It depends on which atom it's bonded to. For example, if it's bonded to F, the nucleus of H would be a lot more exposed because the electrons are kind of closer to F. Is this point clear?
Yes.
Vice versa, if it's bonded to H, Na. Na is ionic, so it gives electrons to H. Now, in this case, the H has even more electrons, like the proton is surrounded by 2 electrons now. So in the first case, the proton is kind of exposed. Like if I show you this is how the first one would kind of look like. So there's going to be a hydrogen proton. And there's going to be a fluorine proton, a fluorine nucleus. And they're going to be electrons. And most of these electrons would be kind of, I mean, fluorine will have 9 electrons. So fluorine had 9 electrons in total. So there would be, most of the electrons would be kind of closer to fluorine's nucleus. Hydrogen would be a lot more exposed because all the electrons would be, hydrogen just had 1 electron. So even that is now closer to fluorine. Is this point clear?
Yes.
And in this case, the opposite would happen. The H is the one that's gaining electrons. So H would, at the end of the day, be surrounded by electrons. So in the first one, the proton of H is kind of very exposed. So it would be a lot harder for it to resonate. In the second one, it would be a lot easier for it to resonate. ठीक है, ये clear है सारा?
Yes, sir.
Yes.
So does it like depend on the electronegativity of the atom?
Yes, it depends on the electronegativity.
Okay.
So it depends on the electronegativity of the atom. So that's what I'm saying, that every time the hydrogen is bonded differently. So you can get by just looking at the resonant frequency, like at what frequency is it resonating, you can have an idea of what element is attached to it. Okay, because whatever element that's attached to it, its frequency keeps on changing according to that. So is this point clear?
Yep.
I said now the next thing is, what do we do with this? So the first thing is we're going to practice like chemical environments. So the rule is, if they have the same chemical environment, if they have exactly the same chemical environment, similar shielding, which kind of indicates that they're bonded to the same atom. So same shielding. So that kind of indicates they're going to have the same resonant frequency. So they're going to have the same resonant frequency. Vice versa, if they have different chemical environments and different shielding, they're bonded to different atoms. So they'll have a different resonant frequency. So for example, if I give you an element like CH4, what do you think? How many different resonant frequencies would this have? Like, are all the hydrogen protons kind of the same, or are they different?
The same.
I mean, they're exactly the same. They both, all of them are bonded to the same carbon atom. The electron cloud that's shielding them, that would be exactly the same. So that indicates that it's going to have just one resonant frequency. So same chemical environment. So so all of them, this H. Remember, we're focusing on the H. The carbon atom would not be resonating because carbon has an even number of nucleons. It's got 6 protons, it's got 12 nucleons. So carbon will not have a net magnetic field. It's the hydrogen atoms that would be resonating. Sometimes they would be aligned with the external magnetic field. If they gain energy, they would be opposing the external magnetic field. So let's do another molecule. What about this one? So how many different resonating frequencies would this have?
3.
2.
So 2 or 3. As a first thing, remember when we talk about the shielding, it's these 3 that are exactly the same because they're all bonded to the same carbon atom. I mean, these 2 hydrogens, TK, are different from, or very slightly. I mean, they're also bonded to the same to a carbon atom. So in that way, they're kind of similar, but they're not bonded to exactly the same carbon atom. It has to be exactly the same environment. I mean, their resonating frequencies would be kind of similar, but this carbon atom is kind of different because its environment is different. So there's just going to be a very tiny difference between these hydrogens. TK, I'm going to color them with some other color. So these hydrogens over here and these hydrogens over here would be very, very slightly different. Is this point clear?
Yes.
Amna, is this clear? Adam, is this clear? And let me just repeat, the point is that these hydrogens are bonded to a carbon atom that is part of a carbon chain. So, I mean, it's part of a carbon chain. These hydrogen atoms are bonded to a carbon atom that's right next to a serial bond O. So the electron cloud would be slightly affected because serial bond O is very electronegative. So maybe the electrons are slightly getting attracted to the oxygen. So these hydrogens would be slightly, they would have a slight shielding difference compared to these ones. Is this clear?
Yes.
So the point is, it has to be exactly the same environment, TK. If it's not exactly the same, then that means it's going to have a different resonating frequency. So I'm going to say that this resonates at F0, this resonates at F1, and then you've got this other one, which is an H over here. That will resonate at a different frequency. Let's call that, okay, let me number them F1, 2, and 3. So let's do another molecule. So what about this molecule? How many resonant frequencies do you have in this case?
2.
Okay, which hydrogen protons will or hydrogen atoms would resonate at the same frequency?
And the CH3s.
CH3 and CH2.
Okay, so these CH3s and these CH3s, okay, remember, they're exactly the same. Okay, the whole environment is, I mean, there's not one bit of a difference. The H is bonded to a carbon atom, which is bonded to CH2, CH2. I mean, these H's, 3 H's are bonded to a carbon atom, which is bonded to CH2 and CH2. So that means these hydrogens and these hydrogens they have the same type of shielding, exactly the same type of shielding. And we're going to refer to that as frequency F1. Or beach में, the middle ones, the CH2s, they are the ones that have similar environment. Okay, again, this H is bonded to a carbon atom, which is bonded to a CH2 on one side, a CH3 on the other side. This H is exactly the same. It's bonded to a carbon atom, which has CH2 on one side, CH3 on one side. So the whole environment around these hydrogen protons is exactly the same. So it would just be 2 frequencies, one for the green ones, one for the red ones. Let's try and do this one. How many resonant frequencies for this one? And which ones?
Either 3 or 4, not sure.
I mean, first one, so here, I think it's going to be 4. So first one is this CH3. There's no other hydrogen proton that's even similar to this one, because there is no CH3 anywhere. You've got hydrogen atoms that are bonded to, the environment is different. So, I mean, this would be slightly different. Then you've got an OH over here. This OH is different from these two OHs because this OH is bonded to a CH2. This OH is bonded to a carbon that does not have any hydrogen. So the environment is kind of different from the rest. So what about then you have this CH2, but these two CH2s are exactly the same. Okay, because this CH2 is bonded to an OH, this CH2 is also bonded to an OH, and both of them are bonded to the same carbon atom, which is bonded to an OH. So the environment is exactly identical. And the two OHs over here, they're also identical. The environment is exactly the same. So that would be the fourth one. Okay, so let's say this resonates at F1, this resonates at F2, this resonates at F3, and you have a resonance at F4. So is this clear? The first thing. Finding the chemical environments. Is this clear? So how is the graph going to be plotted? So you would have 4 resonant frequencies, like radio waves getting absorbed, and there would be 4 of them in this case. One would be, and I mean, F1 doesn't mean that it's a low frequency. I'm not talking about the frequency value at the moment. So let's say there's just 4 frequencies getting absorbed. And this side over here is absorption. Like if I take out my NMR spectrum, just a second. Anyways, this over here, it represents the absorption. You don't have to worry about the y-axis. Just a second. Let me just want to know the name of this. 1 second. Yeah, but what do you call this? I just. So usually the y-axis is not given, but it is absorption of what frequency is getting absorbed. That is what the y-axis is. Now the thing is, which frequency do you think would be absorbed the most out of, like you have F1, F2, F3, and F4. So which one would be absorbed the most?
F1.
Look at F3. How many hydrogen protons are resonating at F3? That's 4, right? Like 4 of them are absorbing. I mean, these 4. F2 is only 1 hydrogen proton is absorbing F1. F4 is getting absorbed by 2. And you've got F1, which is absorbed by 3. So that means the absorption values would be that the ratio would be according to this for absorption. Depending on the number of hydrogen protons. Like if you have more hydrogen protons, the absorption would be a lot more because a lot of hydrogen protons would be absorbing this frequency. Is this point clear?
Yes, understood.
So the
Sir?
height, yes.
Sir, I don't understand why is F4 another environment?
F4. So what is it similar to? H proton or which one is it similar to? I mean, this H proton is resonating, right? Okay. It's absorbing a frequency, its proton is resonating. This H proton and this H proton are exactly the same. Okay. So uski shielding that's different from all the other ones. It's not the same as this one. The environment is different. Do you have any other environment which it's similar to? Like, do you have an OH bonded to a carbon which is bonded to 2 H's? I mean, you do have this one. So these two are exactly the same, but they are different from all the rest of the H protons. Is this clear?
Yes.
So you can't say that it will resonate at F3 because it's very different from these protons. You can't say it's going to resonate at F2 because this proton environment is different from this one. Okay, this one is bonded to a carbon. This one is bonded to a carbon with 2 H's. So just a tiny difference over there. I said, let's do this one as well. The NMR spectrum would be. So your NMR spectrum would be, in this case, just 2 frequencies. There's going to be F1 and there's going to be F2. And F1 will have 6. It would be 6:4. So it's going to be 6:4 in this case, because 6 of the hydrogen protons are resonating at one frequency and 4 of the hydrogen protons are resonating at a different frequency. So that means 6 hydrogen protons, the green ones, would lead to a more absorption of frequency F1. The same would be the case over here. Okay, what's going to happen here is that you'll have 3 frequencies. The first one would have the greatest absorption. So it's going to be 3:2 ratio and 1. So the first one is going to have the greatest absorption, the more hydrogen protons. Okay? Is this point clear?
Yes, sir.
Now, the very last thing about NMR spectroscopy is that each of these peaks, each of these absorption is not going to be just a unique single peak. What happens is that they're going to have splitting patterns. I'm going to talk about the splitting. I mean, I'll explain the reason for that, for a splitting pattern. So each peak that we have mentioned will have a splitting pattern. It's going to have a splitting pattern. The splitting pattern would be, you're going to have a singlet. That simply means a single peak. Similarly, you're going to have doublets. That means it's going to split into 2 peaks. You're going to have triplets. That obviously means, I mean, that single peak that we have drawn above, that's going to split into 3 peaks. And you're going to have quadruplets as well. So that would be 4 peaks. And finally, you'll have multiplets. That means multiple peaks, obviously. A lot more than 4. So, and I'll tell you the rule first. I'll explain this later, but the rule is that if, one second. So the rule is if neighboring carbon atom has n hydrogens, then peak splits into n+1 peaks. So that's a rule. Okay, I'll explain what the rule is. Why is there such a rule? Okay, let me explain what's going to happen first. Then I'm going to explain the logic behind that. And there's some exceptions, except OH and NH2 peaks are always singlets. And don't cause splitting. Now, before understanding what the rule is, I'm just going to explain what is meant by the things I've written. The n+1 rule. Then we'll figure out what's the story behind that. So the n+1 rule is, let's focus on these 3 hydrogens, right? They're resonating at frequency F1, which is this one. The rule is, if the neighboring carbon has n hydrogens, in this case, how many hydrogens does the neighboring carbon have? It's got 2 hydrogens, right?
2.
So the rule is that its peak would split into n+1, which is 2 + 1 is 3. So that means instead of getting 1 unique peak, what you're going to be getting is 3 peaks. That's known as a triple peak. Okay, that's the rule. So over here, the neighbor has, why that happens, I'm going to talk about that later. So in this case, the neighbor has 2 hydrogens. One second. So the neighbor has 2 hydrogens. Hence, this one is going to be a triplet. Do you understand the rule first? Is the rule clear?
Yep.
So what about this one? And remember, immediate neighbor. We're talking about the immediate neighbor. What about these hydrogens over here? How many hydrogens does the neighbor have? Like, it's got 2 neighbors now. 3 on one side, and there is no hydrogen on this carbon atom. I mean, there's literally no hydrogen on this carbon atom, right? So this carbon has exactly 3 hydrogens. So in this case, the neighbor has 3 hydrogens, which means it's going to be a quadruplet peak, n+1 rule, which means that this peak over here would be split up into 4 peaks. Is this clear?
Yes.
And the final rule stated that the OH peak is not going to split, or the NH2 peak is not going to split, and it won't cause splitting to anyone else. Like, there would be no splitting because of this H proton. So you don't have to count this. You don't change this one. That's the rule. Let's also have a look at this one. The CH3 over here, how many neighbors does it have?
Three.
I mean, it's got 2 hydrogens, right, on the immediate carbon atom next door, which is why it's going to be a triplet peak. So that means this big peak over here is actually going to be 3. It's going to be split into 3 peaks. So what about these hydrogens over here? How many neighbors do they have?
Is it 5 or?
I mean, in this case, I mean, if you look at these 2 hydrogens, the neighbor is the 5 neighbors, so it's going to be a multiplet peak. So there would be many, many tiny peaks. Is this clear?
Yes.
So that's the n+1 rule. Just one second. So that's the n+1 rule. And I'm going to apply this very quickly over here as well. This CH3, the neighboring carbon has no hydrogens. I mean, that age, it has no hydrogens. So that means this F1 is going to be a single peak. Then this OH, the OH peaks are never going to split. So that means F2 and F4 are not going to split. What about F3? F3 again has no neighbors. The neighboring carbon has no H atoms. So it's not going to split as well. So all of them are going to be singlets. So is this clear? Is the rule clear?
Yes.
So the question is, why do we have this rule in the first place? So what happens? What happens because of the neighbor? What happens is, let's say I have this molecule, and this molecule is resonating. It's got CH3, and there is a CH2, and there's an OH. So let's say this CH3 is identical. It resonates at frequency F1. And there's this powerful external magnetic field. So we have this powerful external magnetic field. Why do the neighboring carbon atom hydrogen protons matter? They matter because what they do is, and let me just switch just for clarity. So let's say the magnetic field is pointing in this direction. So why do the neighboring carbon atom hydrogen protons matter in the first place? They matter because they're going to cause interference. For example, they would be resonating as well, so they might align with the external magnetic field. So what's going to happen over here? Will these hydrogen protons they would experience a slightly greater magnetic field because of the neighboring hydrogen proton. Is this point clear?
Could you just repeat that as well?
I mean, you had this external magnetic field, right? These hydrogen protons were trying to resonate. They were trying to gain energy and they were trying to resonate, right? So they were trying to gain energy from radio waves. But if the neighboring hydrogen protons are also pointing along with the external magnetic field, these hydrogen protons will experience a greater magnetic field and it would be harder for them to resonate. Is this clear?
Yes, understood.
So the resonant frequency would be slightly higher. Because along with the external magnetic field, you have these neighboring hydrogen protons and you have to oppose their magnetic field as well. But this is not always the case. Maybe one of the hydrogen protons is not resonating. So maybe so one of them is not resonating. So let me just wrap this off. So now the net effect would cancel out. So the hydrogen protons over here will experience the magnetic field, external magnetic field. But the neighboring hydrogen protons, one of them is aligned, one of them is not aligned. So the net effect of the magnetic field that they add up, that would be 0. Is this clear?
Yes.
And the last is that maybe the neighboring hydrogen protons are both of them opposing the external magnetic field. So in this way, the neighboring hydrogen protons would kind of cancel out the external magnetic field. The amount of magnetic field experienced by these hydrogen protons would be slightly lesser. Is that clear as well?
Yes.
So the neighboring hydrogen protons have 3 combinations. They can affect the magnetic field of these hydrogen protons in 3 ways. They could either be aligned with the external magnetic field. So that means the frequency would slightly increase. Or one of them would be aligned, the other one would be opposing. So in that case, there would be no effect, or both of them could be opposing. So in that way, it would cancel out the external magnetic field and the hydrogen protons, it would become easier for them to resonate. So is this clear?
Yes, sir.
So the resonant frequency would change just a bit. So if the neighboring neighboring atom has 2 hydrogen protons, then the interference caused would be in 3 ways, which is why the peak is not going to be a single unique peak F1. It would be 3 different peaks, but they would be very close together. I mean, the effect would be very tiny, but there would be some effect, which is why the frequency is not going to be 1 unique frequency. It would actually be 3 frequencies, and which is why it's going to be a triplet peak. And similarly, if the neighboring atom has just 1 hydrogen, so let's say the neighboring atom has and it's always the immediate neighborhood that matters, not atoms further away, they will have little effect. So you've got the CH3 and you've got this neighboring H proton. So this can affect the resonant frequency of these hydrogen protons in just 2 ways. It can either align itself with the external magnetic field or it can go into an opposing spin. Okay, is this clear?
Yes.
So in 2 ways, it's going to be affected. So that's pretty much it. There's three things in NMR which you have to remember. There's a thing about deuterium as well. We're going to talk about that later. So, and there's some minor issues. So what we can do is we can start with past paper questions. Just to do the first part first. I mean, we've done 80% of NMR. That's about it. The questions are going to be slightly more difficult. So for example, I mean, that's just the marking scheme. Just 1 second.
So could you send us the PDF?
Okay, Bill. So for example, you're given this NMR spectrum. He's asking you to deduce the structure of T. So the NMR spectrum is given below. And so one thing, the questions are always linked with mass spectroscopy, which we didn't do. Mass spectroscopy has two formulas. One is you can find the number of carbon atoms if you have the m+1 peak. So that's a peak that happens in mass spectroscopy. And the formula is 100 over 1.1 into m+1 peak divided by the m peak. Mass spectroscopy is completely different from NMR spectroscopy, but most of the questions are kind of linked. So can anyone tell me the number of carbon atoms first? It's 100 over 1.1 into 0.9 over 20.4. I mean, this is the m+1 peak ratio. Can you even quickly calculate this?
4.01.
So that means you've got 4 carbons. It's already told you it's a saturated alcohol, and it has an MR of 74. So 4 carbon atom alcohol. Let's draw one. These are all H atoms. Now, if you draw 4 carbon atom alcohol, you can just check. And I think the MR would come out to be 74. So 4 carbons is 48 plus 16, that's 64. And there are 10 hydrogens, so that is 74. So you could have this alcohol. But there are other isomers of this. You could have the OH on the second carbon atom. And the rest are all hydrogen atoms. Or what you could have is 3 carbon atoms in a row and a branch, and the rest so the rest are H atoms. So remember 4 carbon atom alcohol, or you could have an OH in the middle. As remember, NMR questions have a lot to do with they've got a lot to do with isomers. Like the information you're given, it's a lot easier to remember. It's a lot easier to do this, or what we were doing over here. Just a second. Where's the? So it's a lot easier to go in this direction. From the molecule to the NMR, it's a lot easier to do that. From the NMR back to the molecule, that's more difficult. So make sure, based on the information that's provided to you, you've got a bunch of molecules, because it's a lot easier to make the NMR spectrum rather than to use the NMR spectrum and go back. So that's why because the information in the table was that it was a 4 carbon atom alcohol and it was a saturated alcohol, no double bonds. So I drew all of them, all the possible structures, all the possible alcohols. All I have to do now is, first thing, the see information that you can get out of this. How many chemical environments you've got? You've got 4 of them. What's the splitting pattern? It's a doublet, singlet, a multiplet, and a doublet again. And the height is going to tell you the number of hydrogen atoms in each environment. So the height is not given, but the rest of the information is given. Now you look at the NMR spectrum, that's 4 environments. Can you tell me, let's start with the first one. How many environments are there in this one? Like how many different resonant frequencies would there be? Like that's 1. So that's 1. Let's call that F1. This CH2 is different from the other CH2s because this CH2 is bonded to a CH3. The other CH2s are not bonded to a CH3. So there's a slight difference. So that's F2. This one would be F3. This CH2 is different from the others as well because this CH2 is surrounded by 2 CH2s. And this final CH2 is different from all the others. So that's F4. And then you've got an OH at the end, that's F5. So is this clear? There are 5 frequencies.
Yes.
So that is, so this is wrong because then the NMR spectrum that he had given us, it only had 4. So what about this one? Let's look at this one. CH3, that's F1. Remember, this CH3 is different from this CH3 because this CH3 is right next to a COH. This CH3 is right next to a CH2. So the environment is different. The 2 CH3s are not exactly the same. So that would be a different frequency of resonance. This would be a different frequency of resonance. This H would be a different frequency of resonance and OH would resonate at a different frequency. So again, I'm getting 5 peaks. So can you tell me how many peaks for this one?
2.
They're going to be 2 because the CH3s are identical. All of them are exactly the same. CH3 next to COH, CH3 next to COH, CH3 next to COH. So they're going to resonate at one frequency, one single frequency, and this OH will resonate at the other frequency. So that's 2 peaks. So our answer is this one over here. Because if you look over here, the 2 CH3s over here, they are exactly identical. Because both of them are bonded to the same thing. CH3 next to CH, CH3 next to the same CH. So that means they're both exactly identical and they're going to resonate at frequency F1. This CH is different, so that would resonate at frequency F2. This CH2 is different, that would resonate at frequency F3. And you've got OH, that is F4. So this one has 4 peaks. Is this clear?
Yes.
We can also check the splitting pattern. Like, what's the splitting pattern? What's the splitting pattern for F1? What would it be? How many neighboring H on the neighboring carbon atom?
1.
So that means it's going to be a doublet. One more, n+1 rule. So what about this H over here? How many neighboring H's for this one? So this.
7.
So there's going to be resonance from this side. There's going to be resonance from this side. There's going to be resonance from the bottom as well. That's a lot of disturbance. So this one is a multiplet. I'm just going to write M over there. So what about this one? The neighboring carbon has just 1 hydrogen. So that's going to be a doublet. And the OH is always a singlet. So here's your OH singlet. You've got 2 doublets and you've got a multiplet in the middle. Plus you can also check for the height. Which one would this be? Like it has a lot of absorption. So which one is this?
F1.
TK, because F1 has a lot of hydrogens resonating at that frequency. So that frequency is going to be absorbed a lot more. So that would be F1. And you figured out the structure. That's how you basically figure out the structure. So you have to make a lot of isomers based on the information, then you try and match it with this. But there's another way of doing this, but that's more difficult. I mean, it's kind of an impossible method. The other thing is, you're given chemical shift values. I'm going to talk about chemical shifts later, but just think of it as frequency. Just think of it as the same as frequency. They don't use the word frequency, they use chemical shift, which is kind of the same. In the data booklet, you're given NMR spectrum. Now remember, this would not be that useful because most of the, if you want to figure out the answer, it's way better to look at the number of chemical environments and look at the splitting pattern and draw as many isomers as you can. And you'll be able to figure out the structure without opening the data booklet. But sometimes you would need to open the data booklet. There are going to be questions which can't be solved without the data booklet. So here are some chemical shift values for typical protons. So if you have an alkane type, like a carbon chain with hydrogens in it, it resonates at 0.9 to 1.7. So these values are provided. So for example, over here, these ones were the hydrogens which were part of the carbon chain. So look at the resonant frequency. It's around 0.9 to 1.7. So somewhere in that range. So everything, it's if there are hydrogens next to an O, it's going to resonate at 3.2 to 4. We did have this. We had this in our molecule as well. This one over here, CH2 next to an O. So F3 should resonate between 3.2 and 4. So it's this one. It's a doublet peak that you're getting in the same range. Is this clear?
Yes.
So let's continue with the more questions. Next time then.
Okay, sir.
Okay.
Right.
I'll try
Thank you.
and send some maybe just wait 1 second. Let me try and find this right now. Maybe there would be NMR past paper video lectures. 1 second. So for example, I think these are past paper questions. And this one is in Urdu, just a second. It's the same question, just us. So I think this one, let me just send this. So yeah, let's continue next time. I've sent you the link of the past paper thing, TK.
Oh, yeah.
Okay, take care, Ethan.
No problem. Thank you, sir.